We can move on to Bobby Jackson next here to talk about Pi SP2. All right.
Hello.
Hey, Bobby.
Hey. So, is my screen being shared yet, or?
I don't see it yet.
Okay, let me try again. That's one. Is it now looking? Is it now there?
Yep, it looks good.
Alrighty. Hello, everyone. So I'm Bobby Jackson from Argonne National Laboratory, and here we're talking today about a open source package for single particle soot photometer data called Pi SP2. So what this is that it is going to be an open source package for looking at black carbon data. And it's important to examine black carbon data because soot particles for emissions can be the second most important contributor to climate change next to CO2. And this is because they are heavily important for direct effects of aerosol direct effects that can help contribute to climate change, as well as aerosol indirect effects on clouds that can help change their microphysical characteristics and evolution. So therefore, we need to be able to have instruments that sample black carbon. And one of them that the ARM facility has used is called the SP2, or the single particle soot photometer. And what this does, so you have individual particles passing through a laser, and you have one detection channel measuring light scattering, and the other measuring laser-induced incandescence. So you get the black carbon diameter and mass, and it collects particle by particle statistics. And in the end, what we're having is that we're getting two signals for the price of one. So we have a scattering signal for black carbon containing and non-black carbon particles, and this will get you the diameter of those particles, the incandescent signal, which happens basically when the particle comes into the laser, and then the coating evaporates off, but then the bottom part lights up, and that's when you get the incandescent signal, where you get the black carbon. And what you could get there is the amount of coating on the black carbon particle, as well as the mass of the black carbon after the coating has evaporated off of the particle. So previously, for the SP2 droplet measurement technology, so they made the SP2 probe that provided software and Igor for processing the SP2 data. So you had to have Igor installed in your system. So it was hard to run on our ADC and Stratus clusters because there was no Igor implementation for Linux, nor was it scalable to distributed systems. Now the problem with SP2 datasets, because they collect thousands upon hundreds of thousands of particles, these could be hundreds of gigabytes a day, just because of the number of particles observed. So we have to process an entire field campaign on a laptop. So he would have a student running a laptop for a few weeks just to do 1 or 2 days. So it became untenable to do operational analysis of SP2 data. So what we try to do is adapt this code to an open source Python package to where it can interact more easily with packages such as Dask in order for scalable processing. So what we call is Pi SP2, and it's based upon ACT that we have talked about earlier in this workshop, and it's based off of DMT's Igor processing code, the PAPI, the probe analysis package for Igor, and it reads in the same files that processes the particle statistics. So if you have raw SP2 data, it will process those same statistics. It can generate time average black carbon mass and size distributions. If you want to link here to the documentation in the repository, it's available at rdoe.github.io/PySP2. It's one of its capabilities is that you can view individual particle waveforms. So what's actually being measured by each probe is that there's a scattering detector and an incandescence detector, and they measure particle signals. What they do is that they measure the intensity of scattered light coming back through a photodiode array as measured by these bins. So what you actually look at here is an intensity distribution of scattering coming off a particle. And when you have a particle scattering generally tends to follow a Gaussian pattern around the center of the particle. So you can tell where the center of the particle is, and by the magnitude, you can tell characteristics such as the diameter of the particle based upon the scattering characteristics. So you can still view these individual waveforms. So you can see one, if you have Gaussian peaks that tend to represent one particle, or if you have multi-peak distributions, that could be, for example, two particles entering the laser volume, and be able to filter out these events using these derived characteristics. So after we had done that, where we had put this into three different phases. So what we had done here with this is in phase one, we've went in and tried to retrieve the black carbon mass from those derived statistics. And then we now go and apply the calibration coefficient and signal filtering criteria to generate unit-based data files. So what PySP2 will support is you can take these calibration data sets that you get from your standard calibration techniques with aquadiode particles, and you can take that data in to derive particle masses and diameters from the raw particle statistics that are generated by PySP2. So, and we see here with our comparisons against the previous code. So what this is showing is the scattering number per cc from the Python code and the original DMT code, that the concentrations are overlapping. The reason why you only see one line here, you can see some very small variability here, but it's very hard to see the difference between the black line and the red line, and that's a good sign. That means that our code is consistent with what the DMT people have been giving us for Igor. And you can take this, we can do customized particle filtering. So as I told you before, there could be artifacts in SP2 data. A lot of it is due to the fact that you could have more than one particle enter the laser beam at once. So that can give you these signatures where you're getting this multi-peak signatures and you can't tell what particle you're actually recording. So a lot of these artifacts can be changed by setting some of these criteria in a DMT global structure. And as I said before, you can do calibrations of the probe. And here, once you calibrate the probe to get your masses, so you basically, what you do is you measure the signal scattered by the particles of no mass, put in your calibration file as your parameter to the DMT global structure. Now, and once you have all this ready, you can take your SP2B data file, your calibration file, load your global structure. Then you just read in the file with pysp2.io.readsp2. You also have a .ini file that the probe will output. You have to put that in there too as an input. Do first your particle statistics with the Gaussian fit function. This will give you your particle peaks, your wave peaks and widths, as well as locations. And these raw particle statistics are then converted into diameters and masses that are more easily interpretable by those looking at black carbon data with the calc_dimes masses function to get your particle size distributions. And here's examples of a couple of different field projects where we've used PySP2 to process ARM-SP2 data. One is from the NSA site, looking here on February 16, 2020, just looking at a time series on the top here of the particle size distribution, with particle size on the y-axis and time on the x-axis, and then the black carbon mass total concentration time series on the bottom. And what you can see here is an approach as we get further along in time, we can see that we have more heavier amounts of soot coming in as we go through the day, indicating that there's likely some smoke entering the NSA site as the day progresses. And you can see most of the particles are generally within under 0.2 millimeter. This should be microns, 0.2 microns here, indicating that, but most of the particles are in a coarse to fine mode aerosol, as we would expect from black carbon. So in the end, we processed entire 10 months available on the ARM archive, about 6 hours of Stratus with Dask used in 216 cores. And the Mosaic SP2 data also available. That's about 2 days for that same load on Dask to process. Just being able to scale this code on the Stratus was a big reason why we converted to Python. And this makes it to where these data sets are now able to actually be put out to the community using the ARM resources that we have. And we are now doing routine processing for sale of this same data set. So here is an example of black carbon mass concentration time series for a smoke event here on the 10th of October, on the 8th of October on 2021. And here we have a black carbon mass concentration time series. And what we can see here is that there's a smoke event in the overnight hours as we approach the sale site. And then during the day, it's after the early morning hours, the smoke starts to leave the area, and then you have lower black carbon concentrations from there. So in summary, we have developed the single particle soot photometer SB2 is to record some black carbon observations that are needed for climate and aerosol modeling. And our current software for processing it doesn't scale adequately to the large size of SB2 data sets. So we made a Pythonic we converted that code over to Python to a package called PySB2 in order to be able to generate the same particle mass and size distributions and be able to be combined with Dash to quickly process NSA and Mosaic SB2 data using the ARM Stratus cluster. And now we're using this for routine processing for Sail and Tracer. And some of our future plans include looking at the aerosol mixing state. So remember I showed you earlier, you could get an idea of the coating thickness through the scattering and incandescent signals. We want to be able to put that as a future task to put into PySB2. And if you have any questions, I would be willing to take them. Thank you. Have a good day.
Thanks, Bobby. It's great to see this out and operational, and it's transparent now of how it's being processed. So, do we have any questions?
Yeah, it looks like we have one. So from Von May, and also we have one from Ian Glenn. So first, I'll go to Ian Glenn. So this is a slightly off-topic point, not a big deal, but a Gaussian fit will always have non-zero kurtosis, right? It's entirely possible for particle distribution of subkurtosis, say fat scales, titties, skinny tails, etc. I mean, you always it could be approximately. I mean, Gaussian works best for this in this. That approximation works better when we look at the scattering channel. Once you get to the incandescence, then we don't rely as much on fits because then it can be off Gaussian. So we just look at more where the peak of the distribution lies within the histogram data. But for the scatter distribution, through the theory, it should be approximately Gaussian if there's a single particle present. And from Fan May, so PySB2, yes, it will support the aircraft SB2, just as long as you have an INI housekeeping file, an INI file, an SB2B file, it should work. And currently, at this point, we don't have current plans to process PySB2 data, to process the previous campaign data, but something we'll definitely look into doing as we have more data available. And another question is it possible to get black carbon mixing state info using PySB2? That is actually our future plan for an ENG that we're going to be submitting this year to get ARM to support. So it will be a future feature of PySB2.
Great. Sorry, Bobby, did you get Henrik's question there about using it with any SB2 instrument?
It should be, yeah, anything, but it should just be anything. It should be any SB2 at all. It doesn't matter if it's ARMS. It's as long as it's just the DMT. As long as it's the DMT SB2, it puts out the same data files.
Okay. Perfect. And then Rick, the last question here that we got. In terms of open hardware, is DMT interested in adopting PySP2 instead of continuing with Igor?
That I'm not sure. I'm not sure if DMT is wanting to continue with Igor on that or not, because I can't speak for what they're doing. I do know the aerosol community in general is interested in moving on to open source with this, but I can't speak for DMT.
Okay. All right. Thanks, Bobby.